about plate tectonics, there are a variety of questions that we want our students to ask and be able to answer. There are questions like, how big are plates? What is the difference in size of plates from the biggest to the smallest? How fast do plates move? And how do we describe that motion of the plates in a way that we can use to solve geologic problems? So we have shown here a variety of simple activities students can do to try to get answers to many of those questions. So for example, the first question is, how big are plates? Well, with the globe, it's really easy to have students calculate and figure out how big a plate is. So as an example, we can use the Nazca plate, which subducts beneath South America, and very quickly determine its size.
Right, so here's our globe. The information on it is the magnetic anomalies of the ocean, as well as topography of the land and bathymetry of the oceans. So we can use those to define our plate boundary. So we'll do the mid-ocean ridge of the Nazca plate first, so we can draw it through the bathymetric high and the youngest anomalies, and we can see offsets in the fracture zones here, the transforms, and we can continue drawing these along the ridge and transforms all along the western side of the Nazca plate, along the ridge here. Okay, and we can finish the mid-ocean ridge boundary of the Nazca plate. Okay, so we've gotten the mid-ocean ridge boundary. The last boundary of the Nazca plate we have to think about is the subduction boundary. That's not associated with any magnetic anomalies, but there's a well-defined trench in the ocean, and so we can see that clearly in the bathymetry on the globe. So we'll just start from the north and go along the bathymetric trench until we've connected here, and we've drawn our Nazca plate.
And one of the key things about, since it's on a globe, there's no distortion. If we did the same thing on our map, we can outline the plates, but to calculate the area becomes complicated because with the map, as we go further to the south, distances become expanded. So on this, we can use a STAME measuring scale, and so we just very simply cut out some squares that students could use to measure the area that is the correct scale. This one is 1,000,000 square kilometers. The larger one is 4,000,000 square kilometers. So we can go through, and actually students could go across and just count up the number of squares and calculate the area of the plate. So that's one of the things we can do. We can also think about other characteristics, length of the ridge, length of the trench.
Right. So we know the size of the globe, so we know its scale. We could print out these transparent scale bars. This one is 2,000 kilometers long, and let's say we want to measure the length of the subduction trench. We could simply count along the trench and see how long this is. Similarly, with the ridge, we could go around here, and we could either measure total ridge segments or transform lengths along the entire plate boundary.
So I think you can imagine that from a classroom point of view, you can have different students measure different plates, the characteristics of them, and then they can compare those measurements to see, is there the same amount of ridge and trench? Which plates have more ridge, which plates have more trench? What are the biggest plates? What are the smallest plates? All the different parameters that may affect how they behave geologically.